Okay, welcome back. We're going to do some statistics, and what we're going to look at is, first of all, where do you find all of the lectures for our class? And so there's this playlist on YouTube, and it's at this channel here, Success for Students. It's at Success for Students at that URL. And when you get here, you can click on playlists, and then you have statistics, lectures, concepts, and AI study guides. So, and then here's the playlist for how to be successful in college and in life. If you're in our class at the college, you have a link to it right here in resources, statistics lectures. So I want to make sure you all know how to get there. And then down here, we have week 1 and week 2. We're in week 2, but we're going to review week 1 and then we'll jump in on week 2. And week 1 is about kind of gaining terminology of statistics and becoming familiar with how you think about numbers. Anybody ever heard about people in Alaska? They have many different words for snow, right? We talked about how different cultures have their own vocabulary. Surfers have their own vocabulary, their own way of talking about things. Chemists, biologists, anthropologists, physicists, sociologists, psychologists, right? All these ists. They're all different cultures. They all have their own language for talking about things. Skateboarders have their own language. And people in Alaska and the Antarctic, they have many different words for snow, many different ways of talking about snow. It's this kind of snow. It's that kind of snow, right? And in statistics, we have many different ways of talking about numbers and data. And so chapter 1 is really sort of becoming familiar with the terminology in statistics, and how do we talk about these different types of data, these different, if we were in Alaska or Antarctic, we'd say, how do we talk about these different types of snow, right? And in here, we're saying, how do we talk about these different types of data? So we learn that terminology, and we have the chapter 1 in statistics, and then I think we also had keywords, and discussion, quiz, data lab, lecture, assignment. I'm not seeing the keywords. Hey, we also have slides. So we'll take a look at the slides also for chapter 1. And then chapter 2 is descriptive statistics, right? Like, how do we take statistics and start to describe numbers? And we saw that example last week when we looked at Gapminder. If you look at a bunch of data, it's hard to make sense of it if you just have a big spreadsheet full of data. But if you visually graph it and show it, it is more consumable, right? So we could see this all as data, or we could see it as some sort of a graph, some sort of a display. And it's easier for us to make sense of it, right? We looked at this last week. And so if you weren't here when we looked at this last week, you could go back into these lectures, this playlist, statistics. And in one of those, we talk about it, and how we're, instead of looking at a big spreadsheet full of numbers, we're creating some sort of a graphic which allows us to more easily understand the patterns of the data. Before we get started, does anybody have any comments or questions? No? So my first question, what? What? That's called Gapminder.org. Gapminder.org. It's a pretty cool graphic, isn't it? Yeah. The health and wealth of all the different nations on the planet, how long people live, and how much they make in each nation.
I like how they did that graphic, how they graphed it out right there with the bubbles.
For sure, the size of the bubbles, the size of the population in each country. And then you can see how much each person makes on average in each country, the GDP per capita, and how long they live. All right, so now we're going to jump into looking just at chapter 1. Chapter 1, we talked about populations and samples and sampling variability, and we had a little data lab where we, had a bunch of data, and then we took a sample from that data, and we calculated the mean. We calculated the mean of the data, and we saw how the mean of the sample, and if we have a sample, it's called a statistic. And if we have a population, it's called a parameter, right? So some measurement of the population is called a parameter. Some measure of a sample is called a statistic. And the sample is going to probably differ from the population. The sample statistic is probably going to differ from the population parameter. And that difference is going to be because of sampling variability. And if we take one sample of our data, we'll get one number. And if we take another sample, we'll get a different number. That's kind of interesting, right? And later in the course, we're going to see how, we could get a whole bunch of samples, and then we could do statistics on all of those samples. So if we, did like, do you want to see that, or you get what I'm saying? It's enough. All right. I think we'll say that. But the main thing here is the vocabulary, right? We have a population, and when we get some measurement of the population, it's called a parameter, and that's the measurement of the whole population. And when we do measure an entire population, we also say that's a census. And then when we take a sample from the population and get some measurement using the sample, that's called a statistic. And the statistic varying from the parameter is called sampling variability. Okay? So that's a little bit there. And we learned about proportions. And a population proportion has the notation of P, and a sample proportion has the notation of P hat. And in our course, we have all of this notation. Here in the resources, you have this sheet of statistics notation. Oh, this might be the statistic lectures. Okay, they're right there. I have them twice. Let's see if that takes us to the same one. Yep, they're already there. And let's make sure this one's working. Go back. Does that one take us there too? Yep, good. Go back. So I only need one of those. I'm going to keep the big one because it's easier to see, because I didn't even see the small one this morning. And so we have statistics notation right here. And the statistics notation here is the population proportion, P, and the sample proportions, P hat. So we have different notation for, different things that we can measure. The size of the population is represented as capital N, and the size of the sample is represented by lowercase n. All right? And what kind of variable is that? 4 levels of measurement. And so the 4 levels of measurement, we have categorical and
Ordinal, interval, ratio.
Yeah, all those. Nominal, ordinal, interval, ratio. And I'm going to edit this because I like saying this slightly differently. We have categorical, and I'm going to call it, I'm going to call it, let's see, qualitative, and that'll be categorical, and quantitative, and that's numerical. Because I like lining up the cues where it's qualitative or quantitative, and you could also think of that as categorical or numerical. And so we looked at these last week, and you've had some exercises on them. But these are just different ways of talking about different things we might measure. And so if we were to measure what, major students were, and we have a population of 24,000 students on campus, what notation do we use for the population? Big N or little n? Right? The size of the population, big N or little n?
Big N.
Big N, okay? So if our population is 24,000, and then we do a sample, what notation do we use for our sample?
Little n.
Little n, right? And our sample is like maybe we do 400, okay? So that'd be the notation that we use if we were doing something where we were measuring the population. And if we ask people what is their major, what's their major, and then we did that with 400 people, what kind of level of measurement are we using here, right?
Ordinal.
Ordinal, why do you think ordinal?
Because it's categories, and the majors are categories. It's not anything, number proportion where it would matter. Or actually nominal, right?
Yeah, nominal. Why nominal?
Because ordinal, instead of nominal, ordinal, it has an order. Nominal, it doesn't have no order. It's just a label.
Perfect. You said that so perfectly. So nominal does not have an order. And ordinal, which sounds like order, does have an order. So I'm going to actually highlight that here. And so there, for nominal, there's no, and nominal starts with n, and no starts with n, right? But there's no natural order. And ordinal does have an order, okay? You see that? Nominal. And so majors, if we were just like biology, chemistry, physics, that's going to be a nominal level of measurement. And it's categorical or qualitative. And then something that would be ordinal would be like who got what grade in the class. Because there is an order to A is better than B is better than C. There's an order to it, right? And then we have quantitative and numerical variables. And quantitative is interval and ratio. And ratio is going to have a true zero. Like what's something with true zero?
Weight.
Your weight, your height. You can't have a negative weight, right? It doesn't go 0, negative 110. Like nobody could be a negative 4 pounds in our known physical universe, right? But you know, or you can have negative money. You could be in debt. So maybe that would be interval, money, or temperature, right? Because you could have negatives, and there is like, you know, things on both sides. But that's interval and that's ratio. So interval is no true zero, and ratio is that there is a zero. And yeah, so that's different levels of measurement. How the samples get picked, sampling method. So then we talk about how do we actually sample stuff out of a population. And sampling things out of a population, right? We have our statistic, which is an estimate of the parameter. And we could draw some sort of a sample, and sort of the benchmark gold standard is a simple random sample. So you just randomly choose people. Okay, or you choose things that you're going to include in your sample, and it's got to be random. And every individual or everything you're choosing to be in the sample has an equal chance of selection. And I'm just seeing if they have sampling variability in here. I'm going to look for variability. Variability. We don't have sampling variability on this page. That's interesting. And so simple random sample is kind of like the gold standard. You could also do stratified. So you divide the population into groups, which you can refer to as strata. And if you look up what does the word strata mean, strata, define. It's the plural form of stratum, which means a layer, level, a series of layers or substance, right? So in geology, horizontal layers of rock or soil stacked on top of each other. Different in society, different social or economic levels, classes or group, different strata or stratum. And so stratified, we divide population into meaningful groups, then draw a random sample within each group. Use it when you want every subgroup guaranteed representation. So maybe we have freshmen, sophomore, juniors, and seniors, and we want to get 25 from each group. So we randomly select 25 freshmen. We think about it in terms of groups, in terms of strata. And we randomly select 25 freshmen, 25 sophomores, 25 juniors, 25 seniors. What's up?
So I have these chocolates, for example, and they are of different sizes, right?
Yeah.
So we could categorize sampling variability, and they're all the same. They're all almond chocolate, right?
Okay.
But they have different sizes. So sampling variability would be it's like a different size and weight of the chocolates, right? And we could do total weight, and then we could analyze all the variability, and we could graph that on Excel and make some sort of like reasoning behind.
Okay, let me show you sampling variability.
How would you apply it? I guess that's my question.
Yeah. Let me show you sampling variability. I actually deleted this data. I think I just have it here in my trash. Let me go get it. So we have this penguins data, and can I just move that back? Move it back to my drive. I got to right click it and restore. There we go. And it should just be right here. There's my penguins data. So here's all this data of penguins. And I'm going to duplicate this sheet. Duplicate. And then I'll work on this one. I'm going to get rid of my charts. They're on the other one. I'm going to select each one. And then I want to do my mean. And so let's say we're calculating the mean of body mass right here. And let me get rid of all this stuff. And I don't need the year. And I don't need that. I'm just cleaning things out. And I want to get my mean and median, and mode. And there's going to be that for the population and for the sample. Okay? And this is for body mass. Okay? So there we go. And the mean is going to be equal to average. There isn't mean here as a function. So, and let me just make this a little bit bigger for you. And we'll just get rid of these also. So everything's on one page. Delete. There we go. All right. So if I go here and I hit the equal sign, everything in a spreadsheet starts with the equal sign. And then I search for a function. I'm going to search for mean, and it doesn't come up. And if I want to read about all the functions, I could go to help. How many people saw this in the previous video? Say aye. And I could go to a function list, and it'll bring me to all the functions. And then on this page, they're all on this page, I could search for Command F or Control F. I could search for mean, and I could just hit these arrows to go through and read about where any time mean is mentioned, you know. And somewhere in here, you know, I'm looking for, like, how do I calculate a mean? And it doesn't have it with average, but average is the same thing as mean. Okay? So in this spreadsheet, Google Sheets, you use average to calculate the mean. We just call it mean in statistics. I'm going to select all those and press enter. And I don't want it to autofill, so I'm just going to close that. So there's my population mean. And now if I want to do a sample, I could create a random number. And I could do equals rand and hit enter. And now I have a random number, and I'm going to fill that all the way down. And then if I look at this, and I could go view, show, and I could show my formulas. And there's also a shortcut for showing formulas, which is control backtick. Okay? And if I show my formulas, I can see those are all formulas. But if I go view, show, and turn off my formulas, I get the results, the calculations. I'm going to highlight all this. I'm going to copy it. And then I'm going to go edit, paste special, and I'm going to paste the values. So I copied the values, and then right from where I copied them, I pasted them as values, not as functions or formulas. So now if I go to view, show, formulas, it just shows this formula, but it no longer shows formulas here. These are just values, right? So I'm going to turn off show formulas. I'm doing that with the keyboard shortcut now, control backtick. Okay? How many people are following me? Say aye. How many people this is a good review? Say aye. Okay. How many people this is a waste of your time? Say aye. Good. And now I could sort this. So I could select all of this, and I don't want to sort that. So I'm just selecting this, and I could go to data, and I could choose sort range, advanced sorting options. And I could say my data is a header row, and I want to sort by rand, and I'm going to just sort it. And now I've sorted these from smallest to largest. So I randomly gave a number, right? And then I sorted, and I'm going to choose the 20 smallest. So that's a simple random sample of 20 out of 344. And I'm going to highlight the 20. So here are the 20. and I'm going to make them yellow. Okay? So there, it's 2 to 21, which is 20. And it should show me if I select them all. Down here, I could change this, and I could see the count is 20. Right? I've got 20. So I've got 20 selected. And now I'm going to do equals average. And I'm going to do an average on these 20. Okay? And I don't want that to fill in. And here is my sampling variability. My sampling variability is, oops, I did it on rand. I got to change this to C. I want body mass. Okay, so I did that now on this column right here. Okay, got the average on the C column from C2 to C21. And that notation, C2 colon C21, means from C2 all the way down to C21. That's what that notation means. Okay, we saw this in previous videos. And now my sampling variability is the difference between the population parameter and the sampling statistic. That's my sampling variability. Okay? And here's what's interesting. I did sample 1, and I'm going to I'll do it this way. And here's this is like sample 1. And then I could do sample 2. And sample 2 will be equal to average. And I'll do the next 20. So before I put that in, I'll just get 20 here. And I'm going to go to count here. Count. Give me count.
You can also specify from cell A
22 to 42, right? Is that count? Is that 20? I don't know why my count is such a crazy number. Boop, boop. We'll make that color. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1. All right. And now I could take these. These are my next 20, my next sample. And I could do equals average. And I'll get these numbers. Okay. And now my sample, and still my population is the same one. So I could copy, well, I'll just do it like this. And now my sampling variability is equal to this one minus that one. And I'm going to make that an absolute reference. So that's my sampling variability. And I could do another sample. And I could get another 20. I don't know how many that is. Let's start over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There we go. And we'll give it some other color. And now we'll do a third sample, and this is going to be average. Whoop. And now my sampling variability is 28. So if I do different samples, I get different measurements because the sample statistic is an estimation of the population parameter, which might not be known. And the sample statistic, right, will differ from the true population parameter, and that difference is the sampling variability. Okay?
You can have a group of humans that are slightly heavier than the other.
That's right. So there's going to be variability when we're sampling between the statistic and the parameter. Do you see that? If you know the population parameter, you could calculate the sampling variability. But if you know the population parameter, then you don't really need to take a sample because you've got the population parameter, right? You don't need a sample statistic. But the concept is important, that your sample is going to your sample statistic's going to approximate the population parameter, but it's not necessarily, probably not going to equal the population parameter. That's just an important concept. And what's interesting? We could do an average of our samples. We could say equals average, and we could say I want an average of this one, and this one, and this one. Right? And the average of that is 4279. And then if we do the sampling variability of that, right, this one's the closest. But there's less variability here when we've taken multiple samples. And so if we took a bunch of samples, like how much can we start to reduce our variability? Or if we do a larger sample, so let's do one that is like, sample 4. And I don't know what size we'll do. We'll do here 1, 2, and watch this. You could grab this little fill handle and you can drag it down and it just completes the sequence for you. Let's bring this down and do a sample of 36, 70. Let's do a sample of 50. Bless you. Very polite. Okay, so now we're going to make this some other color. And we'll make it pink. That's really bright. And now we're going to calculate an average here equals average. And we'll come down here and get all the pinks. And now we'll look at our sampling variability. 101. So it didn't improve a whole lot, but my idea was if we take a bigger sample, and this sample is n equals 50, right? And these samples are n equals 20. And this sample is n equals 20. You start to see the language of statistics, right? We're using this terminology, and the lowercase n means what? Lowercase n means what?
Lowercase n means sample.
It's a sample.
From a statistic.
Sample size.
Sample size.
Yeah.
And then n is from the population, right?
Capital N is the population size. So here we had a sample size 20, sample size 20, sample size 20, sample size 50. And the sampling variability associated with these are over here. I was thinking we might get a little closer to less sampling variability, because theoretically if we did n equals 344, we're sampling the whole population, so there won't be any variability. Well, if we did n equals 343, right, we're going to get really close. So is anybody interested in exploring this a step further? I am. So what if we did this to 100? And let's crank this up to 100 in our sample size. Which is to right there. How many people find this interesting? Say aye. And we'll give it, I don't know, what color haven't we used? Do we use that color? Well, whatever. And now we'll do, this will be sample 5. And sample 5 will be n equals 100. And it'll be equal to the average. And we'll come down here and we'll get the average. What do we do? What color? This one? And then we'll look for our sampling variability. And now our sampling variability is 63. right? So there's less variability between our sample statistic and our population parameter. This is just lucky. And that makes sense, doesn't it? Like the more we kind of get a representation of the population, the more our sample is going to reflect the population. Okay? All right, we'll see if there's anything more here that we want to look at with how samples get picked. So we did stratified. Stratified samples would be like, let's get 25 from each group, 25 from the freshmen, 25 from the sophomores, 25 from the juniors, 25 from the seniors. And by the way, is freshman, sophomore, junior, senior nominal or ordinal? Is there an order to those categories? Yeah, right? So it's ordinal. Okay, there's an order to those categories. And clusters divide the population into clusters, and these are kind of confusing, right? Because one's groups, one's, they both are like groups. And randomly pick whole clusters and measure everyone in them. So a cluster is like you divide people into clusters and then choose the whole cluster and everybody in them. And then we have systematic. So put the population list and pick a random starting point, and then pick every kth individual. So maybe a systematic way would be, right, I have this list here, and they're sorted randomly, and I choose every 10th entry, right? That'd be systematic. And then you don't want to do, like, these types of sampling are to be not trusted. A convenient sample is you just sample that which is convenient. Like you only maybe talk to people at, the grocery store near your house, which isn't going to represent everybody in town, because you might live in the good area, you might live in the bad area. And if you're just conveniently sampling the people in your area, you're not representing the whole town well. Does that make sense? And voluntary response is you let people choose or not choose to complete, the sample. And then bias is this idea that there can be error in our sample or in our sample statistic. And that error could be because, like, maybe we only chose people we like, or maybe we only chose really wealthy people, or maybe we only chose really young people, and that didn't represent the population that we're trying to measure. So it's error baked into the method. So undercoverage bias is part of the population never had a chance to be included, right? We only looked at people, we did convenient sampling and only looked at people in one part of town instead of getting representation of the entire town. Non-response bias, the people who don't respond differ systematically from those who do. Response bias, the wording, setting, or questioner pushes answers. So leading questions, wouldn't you like to be wealthy? Yes or no? Or the question might be, wealthy people have longer lifespans. Would you like to be wealthy? Okay, sure. Voluntary response bias, the opt-in crowd isn't typical of the population. And method beats size. You need to have a good method when you design a study. Okay? Because if you have a flawed method, it doesn't matter how big the study is. And that was proven in, this right here. Right? 1936, Literary Digest did the largest presidential poll ever. It mailed about 10 million ballots and received 2.4 million back, and confidently predicted that Alf Landon would become the president and defeat Franklin Roosevelt. And Roosevelt won by a landslide. And the problem was that, people with cars and telephones skewed wealthy, undercoverage bias, so they didn't cover the population well enough. On top of that, only the most motivated recipients mailed their ballots back, so a lot of people didn't respond. So the wealthy, motivated people responded. So you didn't get a good selection of society, you got a small selection. Meanwhile, the people who are poor, who didn't receive the mailer, they didn't get covered in the in the sample. And then a young pollster, George Gallup polls are still kind of something that happens today, surveyed only a few thousand people, chosen carefully, and he called the election correctly. And even today, they still have Gallup polls, right? So it's kind of interesting. And then we have watching versus doing, observational studies, experiments, and the causation trap. So an observational study is where you just watch and record something, but you can't prove causation with an observational study. So when you measure what people do, right, and you aren't changing anything, like a survey about people's habits, that kind of thing, observational. And an experiment is where you impose a treatment. And a treatment is like, we're going to get one group of people and we're going to feed them donuts every day for a year. And the treatment is giving one donut to a person every day. And then we're going to have another group of people where we don't say anything about their diet. And then we're going to compare those two groups at the end of a year. And what we find when we do that is that the people who are fed a donut every day in our lab, we keep these people in little cages and each day we give them a donut. I'm joking. Ha ha. The people who fed a donut every day gained on average 42 pounds and had health problems. And the people who we didn't do anything to their diet, we didn't give them any kind of a treatment, they were healthier. And so our study would show that if you eat a donut every day, it causes bad health, right? Our experiment, which applied a treatment, can show cause and effect. That's what an experiment is. And you can't do that if you just observe people. If we just observe people who eat donuts, right? Like, how are we, I don't know, or, and it gets tricky because do cigarettes cause cancer? Like, how do you do that study? Like today, there might be there are probably, I'm certain, pretty certain, ethical challenges to doing a study where it's like, we're going to have people smoke a pack of cigarettes a day and see what happens to their health. You can't do that because that's going to be bad for people's health. So you can start to see associations, but to prove something, you have to do an experiment. And a confounding variable is something that you didn't take into account, right? So if you do an experiment, only a randomized experiment can support cause and effect. An observational study can show that two things are linked, never that one causes the other. Okay? The reason is a confounding variable. A third variable tangled up with both of the things you measured. So you can't tell which is doing the work. So, an example of a confounding variable is like, hey, observationally, when people carry umbrellas, it rains. So I'm just going to conclude, my observation is that when people have umbrellas, it rains. I'm going to conclude that umbrellas cause rain. Is that true? Do umbrellas cause rain? No. What's the confounding variable?
That you're only making an assumption when people carry the umbrellas, that's when it's going to rain.
Yeah, and the confounding variable would be clouds.
Yeah.
Right? I didn't take into consideration clouds. Clouds actually cause rain. And then, rain causes people to carry umbrellas, or the prediction of rain. So an experiment randomly assigns trackers to some people, not to others, then compares steps. There's a little example. So that's our vocabulary for chapter 1. How many people got value out of this little review? Say aye.
Aye.
Okay, cool. We'll go on to module 2 next.